Here we are given some XY data and asked to draw the scatter plot for the XY data, as well as the scatter plots for x versus the natural log of y and natural log of x versus the natural log of y. And so just as a preview, the x values will be stored in L1, the y values stored in L2, the natural log of y values in L3, and the natural log of x values in L4. So our first scatter plot will be L1 versus L2, the second will be L1 versus L3, and the third will be L4 versus L3. And so when we look at the data in the first scatter plot, it's going to be unclear if an exponential or power function is the best model. So we move to the second two scatter plots and choose the one that is more linear. For that one, we will find the equation of the regression line and use that regression line together with our knowledge of logarithms and exponents to find the equation for the model of the original data. So let's go to the graphing calculator where I've already stored the data in L1 and L2. We'll move over to L3 and the L3 cell and enter natural log second 2 because L and enter, and then L3 will contain the natural log of the y values. We'll also load L4, going to the L4 site with the cell with the arrows, and hit natural log second 1 since it is going to be holding the natural log of the x values. Now we'll go back to y equals, make sure that we have cleared any of the equations there, and now go up to second y equals, which gives us the stat plots, 1 for plot 1, where we're going to check that it is on and that we are plotting L1 versus L2. So in my case, I'm going to go to the y list here and enter second 2 for L2. I'm then going to go to the window and make sure that my x-min is 0, my x-max is 100, x-scale is 10, y-min is 0, and y-max is 800, y-scale is 50. Now when we plot that, we see a characteristic curve that's concaved up in the right in the first quadrant. It could be modeled either by an exponential or a power function. So let's go back to second y equal and create our second data scatter plot by again pressing 1 for plot 1. But this time we're going to plot L1 versus L3, and so I'll go second 3 beside the y list. We'll go into the window now, and we've just adjusted the y values that are going to be in the scatter plot. So now the y-min should go from 0 to 10 in steps of 1, scale 1. We draw the graph and see that it's not at all linear. So at this point we reject the idea that the original data fits an exponential function, and we will move on to see if it fits a power function. So we do second y1 again and go back and choose plot 1. This time our plot is going to be L4, so I press second 4 versus L3, which you might already have there. Otherwise, enter second 3 there. Go back to the window. The X max will now need to be changed to 10 and the X scale to 1. Now we graph the scatter plot of L4 versus L3, which is the natural log of X versus the natural log of Y. And we've got a linear scatter plot. So we'll find the regression equation by going Stat, Calc, 4, enter L4, so second 4, comma, second 3 for list 3. Press enter. And here we see the regression line. Note A is the slope, B is the y-intercept. We go back to the y equals screen and paste that equation in for y1. So we go var 5 for statistics, over to the right for the equation, and press 1. Now when we graph, we see the equation line going through the plot, and we're satisfied that the correct model is a power function. So now we'll go back to the back to the other screen and choose the power function as the best model, and start to find the power function. That starts with the equation of the regression line for the natural log of x versus the natural log of y, which was the natural log of y equals 1.494 times the natural log of x minus 0.062. We're going to use several of the properties of our logs and exponents here. The first one we're going to use is that the 1.491 can be moved to the exponent of the x, because a constant times a log of x is the log of x to the power of that constant. So we'll have natural log of x to the 1.494 minus 0.062. Now we're going to add the 0.062 to both sides and subtract the natural log of y, which will give us 0.062 equals the natural log of x to the 1.494 minus natural log of y. Now we'll use the fact that the difference of two logs is the log of their quotient, and so we'll just write this as equivalent to the natural log of x to the power 1.494 over y. And now we're going to raise both sides of the equation to powers of e, and so we're going to exponentiate both sides. On the left, we'll get e to the 0.062. On the right, when we take e to this power, remember that e exponentiating base e is the inverse of the natural log. So we will be left with the input there, which is x to the 1.494 over y. Now I'll multiply both sides by y and get e to the 0.062y equals x to the 1.494. And now I can either divide by e to the 0.062, or I can multiply by e to the negative 0.062, since that's the reciprocal of e to the 0.062. So I'll have y equals e to the minus 0.062 times x to the 1.494. And I'll do one more step by actually computing e to the negative 0.062, and that comes out to 3 decimal points to be 0.940. So times x to the 1.494. So our model, our exponential model for the original data is y equals 0.940 x to the 1.494. I may have said that was an exponential model. It is actually a power function that we have come up with as the best model.